Okay, well, thanks for coming. And thanks to Energy Futures and Louise for allowing me to speak in this lunchtime seminar. So the title of my talk is Process Safety and Intensification, which is the name of my group, Research for the Energy Transition. So yeah, Guillermo was just saying that I'm using the new presentation template, which I like very much, actually. I spent about an hour yesterday going through the brand website, looking at the color moods, and I wanted the mood today to be quite vibrant. So today I'm going to go for this particular color combination. I'm only kidding. It's all quite normal from here. So I'm going to give you a quick introduction to the group, what it's about and what we're working on at the moment. About a third of the room already knows this, but for those of you who don't know what I do, I will tell you. And I split this into two parts. So part one is about research opportunities in the energy transition, and I'll frame that with a case study or a parable, if you like, of e-methanol production. Then probably if you've got any questions at the end of that part, I'll stop. Part two is related but distinct in many ways, which is on some experimental work on permeability of polymers to gases at high pressure. So what is process intensification? Well, it focuses on the process of making something, and it aims to use science, the art of engineering and innovation to increase productivity per unit volume or area of process of unit operations, typical things like reaction and separation. So it's aiming to achieve higher efficiency in terms of the space that the process uses, the yield of the products, or the cost of making those products. How you doing? You all right? Improves the sustainability, so reduce emissions, less waste, less energy, less greenhouse gas emissions. And the one that I particularly am interested in, which is more flexibility. So processes that can run in a dynamic fashion, that have multiple purposes and can be distributed at a smaller scale around the regions of the world where they're needed. And this is related to this case study of e-methanol. However, there's quite often some tension between the aims of process intensification, which is to squeeze things into a smaller space, and process safety. For example, highly energetic molecules can increase reaction rate and atom efficiency, so less waste. But typically, these substances can be quite unstable and difficult to handle safely. And compact modular plant can be used for flexible delocalised production, but there's a tension there between the need to separate these hazardous processes from each other and from the public, especially the public. And that is why we combine both process safety and intensification into one theme. So we're working on a few things right now, only some of which I'm going to present today. I'm part of the ICOMIC partnership with Professor Klaus Helldart here, Professor Mimi He in chemistry, and many others. At Imperial and in industry, BASF, Sterling, Mettler Toledo, and several other companies are involved. I'm also developing a flexible reactor platform for material recycling called Economizer. Hi Nick, how you doing? You right? Called Economizer. I'm part of the Halman European project looking at the process safety of manganese ore reduction using hydrogen. And that's with Zeng Nguyen here and Professor Paul Ferdinand in chemical engineering. We're looking at hydrogenation of CO2, which is one of the topics of today, with Inez at the back there and Professor George Potovsek in chemistry. And finally, gas permeability of engineering polymers, with Louis Nguyen at the back, Lorenzo Merlonghi visiting from Bologna, and Professor Amparo Galindo and George Jackson in chemical engineering at Imperial. So the first part of this talk is about research opportunities in the energy transition using the case study of e-methanol. So sometimes you will see plots like this, particularly the Gibbs free energy of various substances. And this might be viewed, without wanting to give thermodynamicists an absolute heart attack, as the propensity of these substances to undergo chemical reactions with each other. I've expanded it a little bit. I put Gibbs free energy on the y-axis in kilojoules per mole, and this is the standard Gibbs free energy at 298 Kelvin. This changes a bit with temperature, pressure, things like that. I've changed it a bit by putting enthalpy on the other. There's no real good reason for that, and there's a general trend. The lower the Gibbs free energy, the lower the enthalpy. But Gibbs free energy propensity for reaction in simplistic terms, enthalpy propensity to release heat. And up on the top right here, we have substances that make good reactants, okay, the less stable substances. So acetylene here, C2H2, you only really need to look at that in the wrong way and it will explode. It's very reactive. And then moving down here, you get to less good reactants, but they still react, and that's key, to things that are good products. And you can see that CO2 is sitting right down here as a good product. So when we talk about using CO2 to make anything up here, we're fighting fundamentally against thermodynamics to a certain degree, but not always. And that's what I'll get into. CO2 can react, and I'll show you how. And actually, water as a product is quite an important way of helping that to react, and using something here like hydrogen to react it with. And overall, you can just about make it work. So why choose methanol for this case study? There's a few reasons. It's a gateway to other platform chemicals, for example, olefins, which are used to make plastics, and acetic acid. The liquid at ambient conditions, and it's been proposed as a hydrogen carrier. It's oxygenated. Each of the two oxygens in CO2 requires a hydrogen molecule to remove. So if your product hasn't got any oxygen in it, you're already using hydrogen, 2 molecules of hydrogen just to make water, which seems a bit of a waste. So leaving 1 oxygen in there in methanol reduces the amount of hydrogen used at the point of manufacture. And finally, it's a commodity chemical, and that enables economic comparisons to be made. So if we work out the cost of producing methanol by some novel route, then we can compare it to essentially the cost of production using conventional routes, which is fossil fuels, methane, and the like. Because when something is a commodity, the price is essentially depressed very close to how much it costs to actually make it. And that's important. So using the thermodynamic data from, well, the NASA Glenn database, that's where I took the pure components values from in that previous plot, you can do some calculations to assess what you might expect if you mixed, in this case, 25 moles of CO2 and 75 moles of hydrogen together and allow it to come to thermodynamic equilibrium. What products might you expect? So this is the molar ratio that you would require to make methanol. But if you do the calculation, allowing the function to make anything, then actually what you find is that, surprisingly maybe, all of the CO2 reacts with hydrogen to form methane and water. And this reaction is called methanation. The delta H is highly negative. That means it releases a lot of heat. And the delta G, the Gibbs free energy change of reaction, is also highly negative. That means this reaction is essentially irreversible. It goes to pretty much completion thermodynamically. Actually, all the CO2 doesn't react here, and the reason for that is there's not enough hydrogen in the feed for all of the CO2 to react. You need 4 times as much hydrogen as CO2 here. We've only got 3 times as much, otherwise it would all be gone. The other surprising thing to me is that actually this is the composition in the gas phase, but at fairly low temperatures, there's a strong thermodynamic driving force to produce solid carbon. Graphite, because that's the data I have, but most likely in practice, some sort of amorphous carbon. And this can be a real problem when you're trying to develop catalysts for this sort of process, because the carbon deposits on the catalysts and stops the reactants from coming into contact with the catalyst. So you need to regenerate the catalyst every so often. So the design for methanation is strong thermodynamically. Fortunately, I guess you've got 4 hydrogens that need to somehow interact with CO2. If kinetically, this can be slow and it can be avoided, but methanation is always a problem, and carbon laydown generally tends to be a problem too in these sorts of processes. If we cheat and we say, well, you can't make methane and carbon anymore, what else have you got? Which is starting to stray into some quite dirty territory when it comes to thermodynamics. Then methanol is formed. So here you've got temperature. On the x-axis, you've got mole fraction in the gas phase. On the y-axis, no more carbon and methane anymore. And you can see that, you know, in your gas phase, around 400 Kelvin, you've got about 20% methanol, which is a reasonable amount. Not loads, but it's some. And you've got the water produced. As you go to higher temperatures, you start to see carbon monoxide, and that is due to something called the water-gas shift reaction, the reaction of CO2 and hydrogen to form water and carbon monoxide. So the reaction forming methanol is exothermic, and the Gibbs free energy change is slightly positive. And you know, as an undergraduate, you'll be taught that that meant that the reaction wouldn't happen spontaneously. It does. You just need to put a bit of effort in to make it happen. That might involve putting some heat in, or not in this case, putting some pressure in the system, doing some work with pressure. Or if you're an electrochemist, just turning up the voltage on your power supply, in which case you can make magic happen. You can do essentially anything, but you just need to make sure to count the number of electrons that are going into your system and the power that that consumes. So this, I will say that CO2 hydrogenation to methanol is a well-established process. It's well known, it's nothing fancy, and that is another good reason for choosing this, because we could do this today. In fact, some people are trying to do it today. So this is a flow sheet from a bit of software called Aspen Plus. It might be familiar to some of you and cause you some nightmares. There's been some controversy recently with the royal family modifying photographs. So I've left the warnings on there just to give anyone who's used Aspen some comfort that it happens to the best of us. The warnings are in the compressors. These are 3-stage compressors with interstage cooling. The interstage temperature is limited to 150 degrees, which is quite normal to protect the seals. And the warning just says that the first stage hasn't reached 150 degrees yet, so there's no cooling in that stage. So that's okay. You look at that warning, that's fine. I don't care about that warning. So we take the hydrogen from the process that we're producing the hydrogen from. I'll get into that later. We take the CO2 from the process that we're generating the CO2 from. I'll talk about that later. We compress it, we mix it together. We recover a bit of heat from after the reactor. This is a classic feed effluent heat exchanger you can see on many process plants. We top the heat up. The mixture goes into the reactor, which contains a catalyst. The catalyst is CZA, copper, zinc oxide, alumina, a classic CO2 hydrogenation catalyst. You can buy it on Alibaba in quite large quantities for not much. Some methanol is produced. It runs at 220 degrees C because that's when there's a good balance between the amount of methanol produced and the rate of the reaction. We recover the heat and then we cool. And because we don't form a huge amount of methanol, we've got a lot of hydrogen and CO2 that didn't react in the reactor. And we could just vent it to the atmosphere, but then all of the work you put into making it is wasted. So we do something called a flash, whereby the liquid, which is water and methanol, comes down here and the gas comes off. And then we can recycle that gas back to the start. So although the conversions of CO2 and hydrogen to methanol in the reactor are relatively small, overall, by recycling the unused reactants, the overall conversion can be quite reasonable. After that, we do something called a low pressure flash. So we drop the pressure, and like opening a bottle of Coke, bottle of fizzy drink, the gas dissolved in the liquid comes out, and then we can recycle that. It's debatable whether or not it's worth it at the kind of scales that I'm going to talk about. And then finally, the methanol water mixture with a little bit of fizz, a little bit of CO2 in there, comes out, and I'm just separating that by a fairly conventional distillation column. So here we have a distillation column whereby water comes off the bottom and quite pure methanol comes off the top. And there's a little trick here to remove some residual CO2. Sometimes people do that in a separate separation column. So the reactor's cooled with heat transfer oil at 220 degrees C. So remember, it's exothermic, and there's quite a lot of useful heat comes out of this reactor. All the other coolers are electrically powered fin fans, or fan cooled with banks of tubes with the process fluid coming through. The compressors are all electrically powered, including interstage coolers, which are also fin fans. And it turned out that there's enough heat for this furnace here and this reboiler here, megawatts of heat consumed, even at the small scales that I'm about to talk about. There's enough heat there from the heat that's produced in the reaction, and also from burning the essential purge stream from the recycle, which contains methane, hydrogen, and carbon monoxide. You need to purge some of the recycle, otherwise things tend to accumulate in the process and cause you problems down the line. Suffice to say, we can run all of this essentially on electricity and CO2 and hydrogen. Okay, and that's why I'm going to talk about running this off renewable energy. So here's the temperature profile in the reactor. So your reactants come in, they react most quickly at the inlet because that's where the concentrations are highest. You see a spike in temperature of about 15 degrees, and then your coolant takes over because now you've got a driving force between the reactor temperature and the coolant temperature. And also you're using your reactants up, or they're reaching an equilibrium, should we say, in this case. This is a fairly typical temperature profile in an exothermic reactor, and this can get easily out of control. Not so much in methanol because of that equilibrium limit, but in other reactions, you need to be a bit careful because it doesn't take much to turn that 15 Kelvin increase into a 15 Kelvin increase and start, destroying parts of your reactor. This uses some established kinetics from Van den Busch and Froment, and you can see people were measuring the kinetics of this reaction back in '96. So, just to show that it is quite an established technology. The gas is hanging around in there for about 30 seconds, so quite quick. And there's about 5 mole % of methanol in the outlet, so a relatively small amount due to the equilibrium limitation. So how do we integrate this into a process that uses renewable energy? So people talk about e-methanol, right? So methanol from electricity, essentially. And this study started by thinking, what is the worst possible process we can think of economically for making methanol? And that is by capturing CO2 from the air at 400 ppm concentration, electrolyzing water, produce the hydrogen. This shouldn't work economically. Okay, it should require so much energy and equipment that it couldn't possibly be considered, in my opinion. But I went into it with a completely open mind as to how it would come out. So we make our CO2 from here, 1 atmosphere, we have to compress. We make our hydrogen here about 20 bar. That gets fed into the CO2 hydrogenation process that I talked about before to make e-methanol. And we chose a small scale, 6,000 tons per year. This is 100 times less than a huge production plant. But the idea was you might have quite a number of these things at various points where a product like methanol might be required for a fuel or feedstocks to a chemical process or whatever. And electricity comes from, in different scenarios, the grid, which is plugged in, although a big plug. It can come from wind and solar, or in scenario 3, wind, solar, and it can be stored in, well, we just use some information off the Tesla website in their megapacks. And I'll talk a bit more about these scenarios. Also, there's the option to store CO2. So when the going is good with your renewables or your electricity price is low, you can capture some CO2 and store it. And the same with hydrogen. If you've got a lot of electricity around, you can electrolyze some water, store the hydrogen for using later. And this is what this plant might look like. So this is roughly to scale. So this will be the CO2 hydrogenation part itself, the reactors, the distillation columns, about 50 by 50 meters, fairly small. Let's say this is located next to the sea, so you put your wind turbines offshore. These take up a lot of space. So here we've got about 6 wind turbines. Here's your solar panels taking up quite a huge area. Here's quite a significant battery energy storage system. All of these are comparable in size to the process unit itself. Your substation might be quite large for the megawatts of electricity that's needed from the grid. Your storage can be quite small, and your electrolyzer and capture units can be relatively small. So a lot of this process is around, supplying feedstocks and electricity to it in terms of the area used. And already you can see from a process safety point of view, you have high pressures and flammable materials here, next to a battery energy storage system, which aren't doing very well at the moment in terms of not catching fire. And one of the fundamental approaches to process safety is separation. And when you have these small scale systems, it's very difficult to, let's say if you're just locating this in a port facility, there might not be a lot of area around to actually separate these systems. But you can imagine easily that a fire on this battery energy storage system might take out your solar panels, take out your process. If you get a high pressure release and explosion, and then suddenly, all you're left with is some wind turbines out in the sea. And this is why we need to worry about process safety. So these, a bit more detail behind the scenarios. So in scenario 1, all of the energy comes from the grid. In scenario 2, the grid can be used, but also solar and wind can be installed, and CO2 and hydrogen storage can be installed. And in both of those scenarios, the CO2 hydrogenation process must run at a fixed throughput of this 6,000 tons per year. It has to always run. In scenario 3, we say, right, what happens if we don't need to run at fixed throughput? What happens if we can adjust the throughput of the process to suit the amount of energy available and feedstock available to run it? Most standard plant can't turn down to 0. So there's some limit, which is called the turn down, that you can run down to before things stop working properly. 20% is not unusual. So you can normally turn a well-designed plant down to 20% of its design throughput, and it will still work okay. And that's the limit we set. Anything below that, if you haven't got enough to run it, it must shut down. And if it shuts down, it takes 24 hours to start back up again. And there's a 20% energy penalty and no methanol production. So it's a big deal to shut down, as it is on a real process plant. In scenario 1, the cost of methanol produced is what it is. It's the grid price, based on the grid price of electricity. For scenarios 2 and 3, the amount of renewables, grid energy and storage is optimized to minimize the cost of production of methanol. So-called levelized cost, that's the essentially price you would charge to a consumer to break even. Your business would make no profit. I won't go into detail about the costs, but just to say that they're all justified. They're realistic, but they're not pessimistic, but neither are they optimistic. And where capital expenditure is required, CapEx, then you have to maintain it, you have to run it. So for the process plant, the CO2 hydrogenation, 10% of the CapEx is required every year to run it, and that ends up being about 1.6 million euros, which some people leave out. And 5% for storage, because storage tanks just kind of sit there. You need to inspect them. You might need to replace them every so often, but in general, they don't need as much attention as process plant. Okay, here's grid electricity price during when we were running the project. Well, up until when we finished the project around July 23, going back a few years. So you can see, things were relatively stable, and then all hell broke loose here, and that's Ukraine kicked off around this point. So we can't really, plan a business off that. If you didn't know that was coming here, I'm sure a lot of people reconsidered their e-methanol projects at this point. But how does this translate to e-methanol cost? That's something that we worked out, and I'll show you later. And I should say we based this on several locations in the UK and Teesside, in the port, and also locations in Spain, Greece, and the Netherlands. But I'm only going to tell you about Teesside, otherwise it's going to be far too much. Here's a typical profile of wind for Teesside, a snapshot really. And here's, it's not so great for sun, it's excellent for wind, as it turns out. But wind is intermittent, just like solar is. It doesn't ever quite go down to 0, not so often. But of course, with solar, you're always dealing with the day and night cycles. And the fact for Teesside, the peak very rarely goes above 1 kilowatt per square meter on your panels. So how does that grid electricity price translate to methanol cost of methanol production in scenario 1? Well, here's essentially the grid electricity price for Teesside converted to cost of methanol. So when the going was good with electricity price, it was around about 1.5 euros per kilogram for methanol production. And this is the commodity price from Methanex. So, you know, it's quite a difference there, but wasn't as bad as I thought it would be for direct air capture of CO2. At the best grid price, the levelized cost of methanol was 1.1 euros per kilogram. And that compares to a range of the commodity price for methanol of 0.24 to 0.57 per kilogram. I thought it would be an order of magnitude higher, and it's double. That's not bad. That's really not bad for this sort of process. And I thought it was quite encouraging. Not that I plan on starting a business to do this anytime soon. However, you can see that when the thing hit the fan with electricity prices, costs of methanol from this process, anything up to about 8 euros per kilogram, which, you know, that's not going to work. Nobody's going to be willing to pay that even for renewable methanol. But that's just plugging your process into the grid. Scenarios 2 and 3 then introduce the possibilities of renewable power and flexible operation. So for scenarios 2 and 3, we used a grid price of 0.126 per kilowatt hour euros. And that gave you a cost of methanol production of 2.8 euros per kilogram. For scenario 2, where there's now an option to build solar and wind power and store CO2 and hydrogen, the minimum cost of methanol production was reduced a little bit, not very much, 5.2 euros per kilogram. And that was achieved by installing mainly wind power, because Teesside's really windy, a tiny little bit of solar power, hydrogen storage and CO2 storage. Hydrogen storage is really expensive. We spent quite a lot of time trying to look into the costs of that. And of course, you need to build your methanol plant and your electrolyzer and your direct air capture plant. But a lot of the cost is storing hydrogen when the going is good with renewables, so you can use it later. Scenario 3, where now the plant is allowed to run at lower throughputs or can shut down altogether when there's not enough electricity available. The cost was significantly reduced. So 1.7 euros per kilogram, significant, over a third reduction. And interestingly, and I should say interestingly, grid power was completely kicked out of the equation here. So it could have used power from the grid. It was so expensive, it chose to install renewables instead. I think that's also quite encouraging, but didn't, you know, make a massive saving, but still interesting. Here, the optimization shows flexible operation entirely over storing hydrogen and CO2 and using battery storage. Okay, so it goes to show that significant savings can be made even with a fairly traditional process plant by allowing dynamic flexible operation. So if you had a process that could go down to 0 but still not need to shut down, just sort of turn over a little bit using minimum energy in a sort of a standby mode, then further significant savings could be made. We haven't done that calculation yet, but we are. So what are the conclusions from part 1? CO2 is relatively stable, but it can react with hydrogen, especially when you're producing water. Methane and carbon solid are thermodynamically preferred, but you can avoid its production due to kinetic limitations. And therefore, you can use CO2 as a source of carbon in methanol and in other chemicals and fuels. The cost difference between e-methanol from direct air capture and electrolysis of water and fossil fuel methanol is not astronomically different. And flexible production avoids the need for expensive batteries and CO2 storage, and especially hydrogen storage. You can get a 35% reduction in cost of methanol production with fairly typical turn down and startup times, particularly for a small plant like this. It's also more inherently safe. If you've not got 350 bar hydrogen storage in your plant, 50 bar CO2 storage and batteries that are liable to catch fire, then it's more inherently safe, following the principles of moderating the hazards and simplifying the layout. So what does this present? I guess the reason for the story is this could well happen. So direct air capture is not the only way to get CO2. You can capture from industrial flue gases, which is cheaper because there's more CO2 in there. If this is happening, it might happen very quickly, and they need to be deployed on a huge scale worldwide. And people who are for batteries or for hydrogen or for ammonia will say that the risks are well known, because liquid hydrogen is used as rocket fuel. Ammonia is used in the chemical industry. But yes, but not at the kind of scales that we're talking about when it's used as energy vectors. And in a sense, these are new technologies, but old hazards. So all the same hazards apply. Things like high pressure, high temperature, high low pressure interfaces, that HP to LP separator in the CO2 hydrogenation process. Actually, here's a fairly classic incident which happened at a place where I worked, although well before I was there. So before the accident, there was a big vessel there, and there's no longer a vessel there. That's a bit of the vessel, which is about 1 kilometre away. And there was a radioactive source measuring the level on that vessel that was never found. It's somewhere in the Firth of Forth. That is actually my office that I first worked in, was about 50 meters from that fragment. Although they unusually for BP moved it by this point. I joined in 2000. So old hazards, new technologies, but you can adapt and improve the methodologies for process safety and design from these traditional industries. There's a lot of work being done and to be done on hydrogen safety. For gaseous storage, people are proposing 350, even 700 bar pressure on vehicles, which is surprising. In order to keep the weight down, people are talking about using lightweight polymer composite tanks. Small cracks and holes in these, which ignite, can result in jet fires. They can extend very long distances, hundreds of meters. Ignition of hydrogen is always a controversial topic. Some releases of hydrogen can appear to ignite spontaneously, but they don't always. To be honest, if you release hydrogen, the best outcome is probably that it ignites immediately, rather than mixes with the air and then explodes. There are a lot of leaks in the traditional oil and gas industries. Not all of those leaks ignite, and surprisingly, that is taken account of in safety calculations. So it might say for a small leak, it will only have a 5% probability of igniting. Obviously, you can just assume it always ignites. However, you then find you have to invest in provisions for safety that would otherwise not be required. But 100% is the maximum, and that's the safest. But is it too conservative to assume 100% ignition probability for hydrogen? I don't know. I mean, I would, but that's the question to ask. And what are the consequences of a release? Let's say you have a hydrogen tanker or a car fueled by hydrogen, which is on fire in a tunnel or a populated area. What are the consequences for the surroundings? And there are projects happening in Europe on that. And finally, liquid hydrogen. So it's used as a rocket fuel by NASA. There's been some issues with it, of course, and some of the hazards associated with it are still not really known. There's one called rapid phase transition, where if you spill it on the floor, it evaporates so quickly, it causes a little explosion before it even ignites. The work for that has been done over water, and they haven't figured out whether it's a problem or not, because the hydrogen keeps igniting by some mechanism that's not fully understood that might involve static and ice and that kind of thing. And batteries. So this is something that Guillermo and I have grand plans to do, and Guillermo has a lot more experience certainly than me in battery fires. But intensification is happening in batteries too. People are trying to squeeze more energy into a smaller space. And unfortunately, to say the least, these batteries are proving quite prone to thermal runaway. There have been a lot of large fires on large battery storage systems already, and I think in South Korea they had so many that they had to put a stop to building new ones until they figured out what the problem was. As well as the fires, they release flammable and toxic gases, carbon monoxide, ethylene, C2H4, and possibly even hydrogen fluoride, which is a worry because it's horrendous stuff. Traditional firefighting methods have a limited effect. If you pour water on it, it just keeps on burning. If you cover it, it keeps on burning because it doesn't necessarily need oxygen to burn. The oxygen is in there already. And it seems to me anyway that there's an over-reliance on active layers of protection. So it catches fire and you put it out, or the temperature goes up and you try to take action to stop the runaway. So are there opportunities for passive protection? Is there something that could be called an inherently safe battery? Batteries at the minute seem to me like a chemical reactor that's running at and above the limit of thermal runaway, particularly when there's a disturbance or damage to the battery. And finally, process intensification. So lots of opportunities here in terms of managing heat and exothermic reactions and improving catalyst design and engineering, catalyst chemistry. Catalysts that are selective against methanation and solid carbon formation. Novel activation technology, which I know Klaus is looking at. Nitrogen and CO2. Nitrogen for producing ammonia. The reason I bring that up, CO2 for what we talked about. They don't like to react very much. You need to do something to them. And the classic way to do that is by heating them up. And there are other ways. So you can use plasmas to energize those molecules and make them, help them react. Thermodynamic limitations can be circumnavigated. They can't be avoided, but they can be circumnavigated through cyclic processes. There are almost endless possibilities. So I think actually part one of my talk might well be sufficient. Looking at the time, you're very welcome to this took half the time last time I did it. Let's have questions now, and I can go through some of the gas permeation stuff if anyone's interested. Yeah. Yeah.
It's not a question. You showed the rough plot of the plant. I it's quite surprised that the CO2 capture plant is quite small.
Yeah.
Compared to the actual plant and also the solar. Do you have any comment? Because at the beginning I asked that maybe CO2 capture plant will be very few.
Yeah.
Because CO2 concentration is very low.
Yeah.
And finally, you show its CO2 plant is small. The react plant is quite big.
Yeah.
The solar panel is also very big.
Yeah. So it's a good question. So the CO2 capture, they're big columns, right? You need big wide columns to get the sort of throughput of air needed to capture the CO2. But that's essentially all it is, right? It's a couple of columns, an absorber, which absorbs the CO2, a stripper, which removes the CO2, a heater. That's essentially it. I mean, some blowers to encourage the air to go through. So there's not a lot of equipment in there. It might be very tall, okay, right? But in terms of width, it's big, but not comparable to the amount of solar panels you would need.
Yeah, but I presume you haven't modeled that separately, right? So you take data from.
Yeah, it's just a footprint from Climeworks, actually. Yeah.
The big problem there is that those are actually not properly designed to create the feeds that you need, right? So there's a lot of polishing that needs to go on. You need to get the water out and everything out of your streams, right? And all these are additional unit operations, right? So I think, and in that sense, the cost probably also, you work with the cost per capture ton of CO2,
exactly,
right?
Yeah,
is actually probably quite wrong at the moment, right? And I think that's where the stakes still lie.
Yeah. So the costs and the footprint are based on information coming out of Climeworks, which is a Swiss company using solid sorbents for CO2 capture. Yeah. So not our bit, but using data from other processes.
Still sit, right? Because they haven't done that detailed analysis like we would.
Yeah. Thank you. Yeah.
was this scenario is generating the green hydrogen on site.
So the hydrogen is generated from water, which is taken from the sea and desalinated. So yeah, that's part of that electrolyzer process, and generated on site. Yeah.
What about importing hydrogen? The other country.
No, it's always, the process will take hydrogen from wherever it comes. So if you want a ship full of, hydrogen gas or hydrogen liquid, then it all depends on what price you get the hydrogen from. So if somehow they manage to produce the hydrogen cheaper, even once you take into account the transport costs, then that will only reduce the cost. Yeah.
I think, but again, if you're looking at distributed systems, right, you're not going to build a pipeline or something.
Yeah.
So anything that would have to be transported then on the network that we have, once you've got lots of distributed systems, you've got a big jam essentially, because you're constantly trying to then distribute.
You're trying to feed it, yeah.
From some onshore facility.
Yeah.
Yeah, to the local site.
So actually, this, if you've got 100,000 ton per year methanol plant, which is the kind of scale that you might see BP Grangemouth when it was still BP, or INEOS as it is now, there it will be almost like crude oil. You take wherever you can get the cheapest feedstock from, and you'll have to take account quality for crude oil as well. But you just, each week you're thinking, I'm going to buy that here, and you would just have these hydrogen ships floating around, ready to go to the highest bidder. And if it makes more sense to produce it internally, you do. And if it makes more sense to get a ship in, that's what you also do. Yeah.
Yeah. One following question.
No, go ahead.
Yeah, you go for it then.
Yeah. Why the about hydrogen? You also show the hydrogen storage. So, but your reactor is always running. It's impossible to remove the hydrogen storage because it's, as you said, it's not safe and expensive and can't find a lot of plants.
Yeah. Well, not only is it possible, but it's optimal in the case of scenario 3 to remove the hydrogen storage, and that is purely on an economic driver. I haven't built any considerations about process safety into that. You could say that there's a 1 in 10,000 year chance that this storage vessel will explode and kill 10 people, and then dubiously try and put some sort of economic cost on that incident. But you don't need to. Purely on market economics, hydrogen storage is just too expensive at the moment. It's nowhere near cheap enough to consider it. Yeah. Guillermo was next, and then Kaiser.
Yeah, super interesting, Chris. Thank you. So you talk about all these processes bringing different elements and safety. And then you kind of partially answered the question, but you didn't convert the safety into a cost.
No.
Okay. No.
Well, we do for other things. For example, in laying out plant, there's a tension there between trying to make the plant compact and not taking up too much space. But if things are too close together, then one thing catches fire, the whole thing goes. Yeah. So there is something that we have where you can optimize the layout. Actually, Kaiser was involved at the very early stages, where you optimize the layout considering the cost of safety, the cost of the lost units should they be caught in a domino effect, and again, dubiously, the financial cost attributed to the life saved. Yeah.
So then that was my question, because you alluded to safety quite often, but I was not sure if you had in this analysis included the cost of safety, because most of the time I work with buildings and forests, and the cost of safety is not like in a chemical plant, it's by regulation.
Yeah.
As people go and they bring as little safety as they can get away with.
Mm-hmm.
And I wonder if that's what they're doing in chemical engineering or not.
No, it's not to that level. It needs to be justified. So you will work out, for example, the frequency of an event where one person loses their life, 10, 100, and that frequency must be below some tolerable level. And that level tends to be very low. So 1 in 100,000 years, 1 in 10, a million years for big, large fatality events.
Who puts that number?
The Health and Safety Executive in the UK. And it's the For the big plant, it's the COMA regulations, the Seveso directive, which came in after some big incidents in Europe and the UK, to start to establish that sort of approach to safety. So there's a level where if you're at a certain frequency that's too high, you have to do something no matter what the cost, or you close your business down. There's a level, a range where you have to say that the cost of additional safety measures isn't worth it in terms of the reduction in risk, fatalities, for example, which is always, when you're working at 1 in 100,000, 1 in a million year events, actually that cost isn't huge, because you're talking about, 10 people being killed every million years is very low. So reducing that to 1 in 10 million years, it's very difficult to justify at that stage from this approach, morally maybe. And then below that level, you don't need to do anything unless your competitors are doing it. So if the plant next door making methanol is doing something, the regulator will expect you to be doing it as well.
But they will have to come and visit you and say, oh, but so I look.
They check you. You make the case, and they come in and they go through the case very carefully.
Safety. In my world, it is like this, and I'm sure in yours, well, you are much chemical engineering, much more mature about safety. Is that I look forward you bringing these new technologies. All of them have hazards. Wind turbines get on fire, even solar gets on fire.
Yeah.
I say too many fires anyway. But when you bring them all together, I wonder when you do the cost analysis, what is the problem of not understanding these hazards, but people asking them to be in the power?
Yeah, I don't know.
It will be amazing.
Yeah. Yeah.
Study safety work. So like when you do your initial design, do a design review, and do a hazard probability study, and they inherently safe at that stage of design, saves you, millions if you had to retrofit, say, a trip system or a depressurization system or something on a live hazard once you're in operation and a hazard's been discovered, basically gets an order of magnitude more expensive to manage that hazard compared to design it out.
That's when the conversation gets amazing, because then if you want to bring back just batteries, you want to bring massive batteries into your power plant, you're aware that the batteries are next to the flammable. Where do you get your data from? How do you get up with the frequency of battery? Now you have to go to South Korea.
Yeah.
Because they are the only ones who are not hiding away from this happening.
Yeah. And if you use that data, you wouldn't build a battery storage system anywhere.
And if you go to, I went to get Egypt. Egypt had 0 ignition. Oh, amazing. You should use that data because they have no ignition. So because if you have to go to other countries, you depend on the media almost to see what these are happening. And then the uncertainty in the frequencies changes our economics completely.
But I might be wrong, but I thought one of the major problems with the South Korean BESS systems was basically the accumulation of gases, and then when you open the doors to emergency response.
We all learn things from accident happening. But when it was designed, no one knew about this.
Yeah.
They start to blow up. It's like, what could it be? Oh, we just learned something. Okay, guys, don't decide. It's design direction based on surprising accidents. And in the meantime, everybody else is buying the system that was to say.
They didn't have a chemical engineer.
And lastly, we are working on this, and we are working with chemical engineers.
Systems and learning systems to make the atmosphere safe for entering, like all of that's very standard in.
100%. I couldn't argue one more with you, but you will be surprised how people are surprised that these things catch on fire. And it's not that they are lawyers doing this. These are professionals that are install these units with amazing pamphlets, and they install them, and then after 5 weeks, suddenly one of them catches fire. Now the ones in California are not catching fire, but the ones in your plant are catching fire, and they are supposed to be the same.
Yeah. Okay. So much as I would love to talk a bit about gas permeation of polymers, I don't want to use up all of your lunchtime. I love the work. And ironically, part 1 was really not the core activity of the group. Okay. It's a case study which shows that it's going to get real. And the group is experimentally led. And this was some work on that side of things. I'll have to come back or find a reason to give another talk on this. another time.
Could you give us 5 minutes? All right.
You sure?
Yeah.
Go on then. I like your interest, Guillermo. So it is related to what I just talked about, and in particularly for the storage and transport of hydrogen and CO2. So there's talk about using existing infrastructure for some of this purpose, and it's all in carbon steel. And CO2 corrodes that like nobody's business, especially when there's water present. And hydrogen, maybe not for mild steel, but hydrogen embrittles some metals, and there can be a very sudden fracture and loss of containment under pressure. So people are talking about using polymers and are using polymers to protect these underlying metal components from corrosion, and as the storage vessels themselves. So for onboard vehicle storage, I mentioned here's a composite tank, lightweight composite tank for storing hydrogen at 350 bar in a vehicle. Otherwise, the metal's just too heavy. This is a big bit of flexible pipe that goes underneath the sea and, well, transmits oil and gas from the seabed, or CO2 in the reverse direction if you're talking about CO2 storage or enhanced oil recovery. And, you know, any of us who are working in this sort of area will have a lot of polymeric materials around. So O-rings, backup rings, bearings for rotating machinery, all made of polymers. And this is the classic beige PEEK polyether ketone, which is a material that we've looked at in this work. So permeability is interesting because it's a combination of two things. One is the solubility of the gas in the polymer, which is a thermodynamically predictable quantity, and the diffusivity of the gas in the polymer, which is a kinetic property. So again, talking about thermodynamics and kinetics. And it can cause a problem because if the gas permeates through the polymer, it can expose the metal to corrosive substances, which is what you don't want. It can lead to the accumulation of flammable and toxic substances in places where you didn't expect it, if it's not ventilated properly, and therefore fatalities and explosions and fatalities. If a large amount of gas dissolves in the polymer gets bigger, it swells, and that can cause it to fail and the gas comes out, which is a problem if it's flammable or an asphyxiant like CO2. And if the polymer is containing a lot of gas under pressure, then when you depressurize the system, the gas inside the polymer can't get out quickly enough, and that causes the polymer to essentially burst open and be completely destroyed. That's rapid gas decompression. Unfortunately, it turns out polymers are extremely complicated, especially the ones that we're looking at, which is semi-crystalline polymers. They consist of in a region of sort of disordered polymer that hasn't had time to arrange itself in a nice ordered low energy state. This is called the amorphous region, and distributed within that are these crystalline regions where your polymer is nice and aligned. If you put it in an X-ray diffraction instrument, it will give you some nice peaks where, you know, the lamella are quite evident. Generally, it's assumed the crystallites are not permeable, or don't directly contribute to the permeability. Unfortunately, as I now know from Louis' work and McKeely, there is an interaction between the crystalline region and the amorphous region due to these sorts of features that affect the behavior of the amorphous polymer. In particular, they depress the solubility of the gas in it below what you would expect from thermodynamic calculations. So Lorenzo is visiting from the University of Bologna, and they do all this sort of work looking at the statistical mechanics of this sort of arrangement. But the amorphous region itself, I will try to give it to 5 minutes. It can be glassy, so a cool polymer where polymer strands aren't moving very much. That's why they're stuck in this amorphous state. We'll be done in 2 minutes. And a rubbery state where the polymer is a little bit more mobile, and this tends to correspond with the difference in mechanical properties, where it's a bit stiff and then it's a bit more bendy, hence the rubbery. The glassy phase is quite difficult to model. The rubbery state, which is at equilibrium in its lowest energy state, is still difficult, but less difficult than the glassy polymer. We are interested in measuring this rate of permeation up to pressures that are relevant for the storage of CO2 and hydrogen. And for this, we developed this here, which is a permeation cell with a polymer sample squeezed between it. That works quite well and has been adopted by the National Physical Laboratory for high pressure permeation experiments. They don't know that it was me that designed it yet, but I'm slowly trying to break the news to them. So here's some typical measurements. So you pressurize the polymer, you wait some number of kiloseconds or hours, and then finally the gas, CO2 in this case, breaks through and appears in your analyzer. And these curves are the fundamental measurement in the permeability of polymers. So this is for CO2, a high density polyethylene, a flux of CO2 per unit area of order of magnitude 4 times 10 to the minus 5. For peak, order of magnitude 1 times 10 to the minus 5. For Viton of fluoroelastomer, much bigger, at 1 times 0.5 times 10 to the minus 3. So they all have very different permeabilities, the CO2. So what I will skip through is the modeling of these curves. Suffice to say, we can explain quite nicely the process of permeation of CO2 through polymers, where the polymer expands and the diffusivity of CO2 actually gets higher as it permeates through because it opens up the polymer structure. Louis, at the back, is working on his PhD with Amparo Galindo and George Jackson in ChemEng and myself, looking at the modeling of solubility and diffusivity in polymers using the Saft gamma me equation of state. That allows you to predict solubility if you have the right parameters. And the nice thing about this equation of state is that it is a group contribution theory. So you can actually break polymers down into their constituent groups, CH2, aromatic CH, COO, and build up your polymer like that theoretically, and then predict solubility. And the work that Louis has done, it works amazing for polystyrene. Not so amazingly for PMMA, but this is with no changes to parameters. And the parameters amazingly are estimated by looking at molecules, volatile molecules that feature these groups. So not polymers at all. So very powerful equation of state, and Louis is developing that further. And finally, this is very recent work, as in yesterday. The results were measured. Lorenzo is visiting from Bologna to measure the permeability of polymers to hydrogen. And for now, because they're very similar in size, we're using helium for obvious reasons, that it's much less hazardous to pressurize helium to 500 bar as it is to pressurize hydrogen to 500 bar. And the permeabilities are quite similar. You know, they're the similar kinetic diameter, neither are polar molecules, so they don't dissolve in the polymer to any greater degree. And now therefore have a similar range of diffusivity and solubility. So this is the very recent result that I pasted in this morning. HDPE, so at 100 bar, ambient temperature, the flux is of order 1 times 10 to the minus 5. And if you remember, the CO2 flux was 4 times 10 to the minus 5, so 4 times lower permeability to helium in this HDPE, a different sample actually, but same material, than CO2. And Lorenzo was also interested in something called PA6, which is the polyamide or nylon. We would know that more familiar as, which has low permeability. So probably a bit more expensive engineering polymer, but more appealing as a liner in H2 storage tanks because of its lower permeability. So that is all that in a nutshell. I really like these experiments and I really like the analysis, which is why I wanted to present it today. So obviously I need to give credit where it's due. So these are all the people that helped with this work. So actually Hidde Kohlmeier, who did the work on the e-methanol, he is now doing a PhD at ETH Zurich, and these others. So thank you very much. Sorry for rushing through the second part. Thank you. I assume you don't have any questions.